Hello, my name is Hugo Gaggioni. I am with the Professional Solutions Group of Sony Corporation of America, and I'm here to explain the introduction of a new compression algorithm that we call XAVC, and is the highest level of implementation of the advanced video coding technology of H.264 or MPEG4. This is the agenda of the topics that we'll be discussing today, with some background of how the algorithm works and how it is used in our professional products. XAVC is essentially a brand name that Sony uses to define or to describe an implementation of an established codec called H.264. We discovered during the last 3-4 years that the world is moving very rapidly toward adoption of video signals that are going beyond the capabilities of high definition. We are now rapidly going into high frame rate and 4K, and also images that have very large dynamic range and color gamut. And therefore, we are almost exhausting the capabilities of existing codecs, and we had to implement a new one that will give us sufficient efficiencies to implement newer applications and products. Okay, what is XAVC? XAVC is the implementation of the MPEG4 H.264 advanced video coding at the highest possible level of implementation, level 5.2. MPEG4, as you probably know, is a family of compression systems that have been defined by the ISO and the ITU, and I'll come back to that later, through the years. And for example, part 2 of the MPEG4 family is what is known today as the SR codec, or simple studio profile, that we had in our SR machines and servers. Today, we decided to implement XAVC as the highest possible implementation of the algorithm of MPEG4 part 10, or advanced video coding. This algorithm, XAVC, is fully compliant with every specification of the H.264 specification, and capable of reaching the maximum level of performance and efficiencies, and covering from 420 all the way to 444, and the largest number of raster size in terms of pixels, as well as bit depth. It's an open format. There are many implementations in the market at different levels of complexity. But the implementation that Sony embarks in XAVC is capable of reaching up to 4K and at 60 frames per second. It's the fastest and largest implementation of the algorithm. Also, the algorithm is capable of using 8-bit, 10-bit, up to 12-bit. And the codec is wrapped into a file format, which is the MXF, specifically operational pattern 1A. In order to make this algorithm practical, Sony developed a research program to create a single chip, a single custom ASIC, with very low power consumption. This device is not only an H.264 or XAVC compression engine, but it's also an MPEG2 compression engine, so that when we implement or install this chip in our product, the end user has the capability of selecting whether to continue using MPEG2 or at its own decision, move to the implementation of H.264 or MPEG4. The bit depth is 10-bit, and as I said, it's capable of reaching pixel sizes of up to 4K by 2K, and also high frame rate. Specifically at high definition and 2K raster sizes, the device can operate up to 180 frames per second. Okay, how do we position this algorithm, the XAVC? As you know well, Sony has done extremely well, and the industry has benefited extremely well from the use of the SR codec, or in other words, the MPEG4 simple studio profile. This is a mastering codec that continues to be used in the market for high quality HD and 2K mastering for TV movies, dramas, and program exchange. And also because it's capable of right now to reach RGB at 12-bit precision, and accompanied in our implementations with 16 channels of audio. At the other extreme, we have MPEG2, which has been extremely popular codec. It's a workhorse of the industry. It is probably the most adopted compression algorithm embodied in the family of XTCAM product, and it continues to become a workhorse format for news production, for drama, for a mainstream magazine production. Therefore, this will continue in the future because of the heavily installed base of products that we have with MPEG. XAVC comes into play in applications that cannot be served by either one of these two previous algorithms. We need to reach high frame rate. We need to go to 422, 444, and even 10 bits, and densities in pixel size approaching and reaching 4K. Therefore, these are beyond high definition applications that will be perfectly covered by the use of XAVC. This is the universe of possible data rates and pixel formats and raster sizes that the algorithm can cover. We begin from proxies. We can create proxies, videos at very low data rates using the long GOP or multi-interframe compression, passing through HD at data rates of up to 440 megabits, either in intra-frame or inter-frame compression, and the maximum capability will be to reach 4K at 60 frames per second, with a maximum data rate permissible by the algorithm of 960 megabits per second. Again, the implementations of this algorithm can be selected to be intra-picture or intra-frame compression, or long GOP or inter-picture compression. All right, also I'm going to give you some of the results of the investigations that we have done around the world in the trend of data rates and configurations for codecs for future applications. In news production, although MPEG2 in the long GOP is heavily implemented in the market, there is a trend to try to reach higher picture quality, moving to 10 bits and 422, and if at all possible, trying to lower even further the data rate, in other words, reducing the file size. It's a trend. Many broadcasters around the world would like to see this happening with future technologies. Other broadcasters, the different regions in the world, would like to transition to 1080 full high definition at 60 or 50 progressive, but they don't want to pay the prices of higher data rates like 100 and 200 megabits per second. Their pipelines have been defined and they enjoy the economies of 50 megabits per second. Therefore, there is a search for a solution that will give me 50 megabits, 1080, 50 or 60 progressive, which until now has been very difficult to achieve. And also, in other parts of the world, some end users would like to ease the complexities of editing and trying to move away from the perhaps complexities of long GOP and try to do intra-picture compression and unifying production completely, not necessarily acquisition, but production using intra-frame techniques. Therefore, these are general trends that exist in the market in different regions of the world. This chart will describe how XAVC has grown from the initial implementation that we had and what we envision for it in the future. Notice that the vertical axis describes the complexity of the pictures in terms of pixel density and 4K or high speed and high frame rate. The lower end will be the conventional high definition interlace. And the horizontal axis describes data rate from low number of megabits per second all the way to high number of megabits per second. Originally, when XAVC was implemented last year by Sony, the first place that we decided to use it was in our high-end digital cinematography cameras, the F5 and the F55. In those cameras, XAVC could reach up to 600 megabits per second, limited by the power consumption of the camcorder implementation. And using intra-frame compression, we could do 1080 interlace, so 720 at 60p at 100 megabits per second. That is also intra-frame compression. We could do 60 progressive 1080 at 200 megabits per second. This is simply utilizing intra-picture compression, no inter-frame or multi-picture compression. On this side of the picture, we have now the conventional, the well-established MPEG2, which is a long GOP, long group of pictures, which today exists up to 50 megabits per second. Also, there are implementations of 35 megabits per second, 25 megabits. But it would be very nice, and it will create a lot of cost efficiencies if we could launch an XAVC long GOP. At 422 with 10-bit, we could reach at 35 megabits per second picture quality levels that will surpass probably what MPEG2 can do today, even at 50 megabits. 50 megabit long GOP XAVC fulfills the dream of moving to 1080 50 progressive or 60 progressive within the efficient pipeline of 50 megabits per second. Therefore, this is another milestone that we can reach using the XAVC. The 600 megabits per second intra-frame that XAVC demonstrated in today's F5 and F55 cameras can be alleviated by reducing the data rate to 150 megabits using long GOP. That will enhance the duration time in the recording in our memories. And also, long GOP implementation of XAVC can be used to create proxy videos at very low data rates, which are ideal for wireless transmissions and streaming. Very specific to the Sony implementation, because as you know, the ISO and the ITU, or definitions of compression systems, only define the syntax and the decoding rules of the algorithm. The complexities or advances in the encoding technique are left to the imagination of the manufacturer. And Sony has enormous knowledge in creating compression systems. In the encoding chip of the XAVC, we implement something called a two-pass encoding, but we do it much faster than real time. We actually analyze the pictures and segment and describe what areas of the pictures are complex, are flat, are easier to compress, more difficult to compress, and we distribute the amount of bits that we have at our disposal in the most optimal manner to produce extremely high levels of picture quality in a pre-analysis. And then when the frame comes in, we will apply those decisions to the video. This type of techniques allows us to create a lot of metadata describing the characteristics and the statistics of the different elements in the picture frame by frame. And this information can be passed from compression cycle to compression cycle, avoiding the traditional degradations that we find in multi-generation work in conventional codecs. Therefore, even after a number of cycles of compression, the picture quality of XAVC maintains very, very high, and compared to other implementations of H.264 that exist today in the market. Now, let me give you a little background on the actual creation of H.264. It's going to be very brief. We can be here for a long time talking about this implementation. As part of the activities of MPEG4 back in the early 2000s, there was a desire to unify the activities of the International Telecommunication Union and the ISO, the International Standards Organization, in creating a new algorithm that will surpass the capabilities of MPEG2 back then. In 2003, a joint video team of researchers developed what is now known as H.264, or Advanced Video Coding, or MPEG4 Part 10. All of these names mean the same. This is a very complex algorithm based on the same structure of compression that we had in MPEG, but now with much more sophisticated compression tools. This is called an interframe or hybrid DCT architecture, where we have embedded multiple frames of references that will be used to predict incoming blocks of pixels. And each one of these areas, the algorithm had enormous technical tricks in order to improve the picture quality. Then natively, this is an interframe or long group of picture algorithm. And as I said, depending on the application, you could use different tools that are permissible and described in the algorithm. We are not going to discuss them, but all of these techniques, or the selection of these techniques, gives rise to different profiles, modes of operation of the algorithm. And one specific profile, which is very important in professional applications, is the high profile. High profile began with 420 and 8 bits, but very quickly advanced into 422, 10-bit, and now 444 and 12-bit. This is the profile that defines what techniques can be used in professional applications. Also, how fast you can run and how large the images, the parameters of the images, will define a level of implementation. Therefore, we have the traditional profile and level combination that describes MPEG algorithms. XAVC is implemented at level 5.2, which is the highest permitted by the algorithm. In its generic form is long GOP, but if I were to disconnect the interframe portion of the algorithm, the XAVC becomes an intra-frame compression. Therefore, the chip or the implementation can be easily switched between intra-frame compression, where compression takes place on a picture-by-picture basis, or long-up or inter-frame compression, employing all of the techniques in the algorithm. Now, these compressed bits have to be contained somewhere, and that somewhere is a file format called the MXF, the Material Exchange File Format. And this is the structure of the file format. It has a header, it has a footer, and you notice we have areas where we can place metadata in the beginning of the file, and we have edit units. These edit units can be a compressed frame or a compressed series of frames, a long up. And there is now a specification to identify all versions of AVC or H.264 to be contained within the structure of MXF. Now, going a little bit deeper, and I want to mention something that's very, very critical and very important and unique to Sony in this regard. These edit units can be, as I said, intra-frame or inter-frame compression. And there are two flags, the sequence parameter set and picture parameter set, that are defined in the beginning of each one of these edit units. The purpose of these sequences, of these parameters sets, is to describe the behavior of the codec, or the behavior of the signals that are to be compressed by the codec. It can be macro characteristics. I'm doing 720, I'm doing 1080, I'm doing 50 Hertz, 60 Hertz. Or it can be more a detailed description of how the algorithm is operating on a block-by-block basis inside the picture. Sony implements this description of the metadata on a frame-by-frame basis. Therefore, if the scenes and that we are shooting changes dynamically during the recording of the clip, I can flag in these parameters the behavior of the codec, because the codec is dynamically changing depending on the characteristic of the video. Therefore, on a frame-by-frame basis, I now have the capability to tell the decoder how my encoding cycle is behaving, as opposed to just define it once per clip and not being able to reach the maximum picture quality by not having this dynamic characteristic. Therefore, this is very unique to the MXF file implementation of that wrapped XAVC. In terms of image quality, one of the initial objectives of XAVC was to try to alleviate the weight, the heavy data rate that was in place in our electronic cinematography cameras. For example, a single frame of RAW of an F65, which is an 8K camera, is 10 megabytes per frame. Then you can imagine very easily during the course of a movie, you accumulate terabytes of storage. An F55, which is a 4K camera, is about 5 megabytes per frame. Still, lower weight in terms of data rate and file size compared to the F65, but still somewhat heavy, especially for broadcasting operations. XAVC at 4K is just about 1 megabyte per frame, which with a picture quality that can rival easily the picture quality of the raw signal of the F55. Although I might not be able to see it properly, but we've done a lot of experiments, and this is an example of a raw frame that was captured at 4K at 24 frames per second, and we graded using an S-log gamma and inside a S-gamut color space, and we completely performed the same shot using XAVC at 240 frames per second. This is 4K, 4096 by 2160 lines at 240 megabits per second for 24 frames. And the picture quality, even projected in very large screens, is identical, visually lossless, even for the golden eyes examining the picture. Sony planned to introduce XAVC in many products that we have planned for the future. We began with an XAVC specifically designed for professional applications, but we are now also opening to consumer applications, and we're going to signal or define the use of XAVC in the consumer space by using the name of XAVC-S. This XAVC-S will be limited to 420 and it's a long GOP. It doesn't have the freedom quite yet to move to intra. We don't see that happening in the consumer space. And also the file format is going to be MP4, not MXF. And also in proxies, when we do proxies for wireless transmission, we will employ MP4 file wrapper as opposed to MXF. Then XAVC-S is constrained to be long GOP and MP4, while XAVC can have the freedom to be intra or long GOP implementation. Here you see the market segments that currently we envision for different levels of picture quality, from high budget productions to wedding videographers, for artistic productions, for news gathering. And today, or until recently, Sony was addressing the needs of this application, employing in the high end the SR codec and of course RAW in the form of F65 and F55 RAW. And for the bulk of program production, broadcast production, and even prosumer applications, we were employing the MPEG2 in high definition form. Now, with the introduction of XAVC, we're going to complement these previous codecs, allowing us to create new efficiencies as we approach very high levels of picture quality and data rate, or reduce the data rate and enhance the picture quality as we move to the prosumer and consumer levels. Hence, the end user now will have capabilities at the click of a button or inside the menu of our product to select different codecs, either to maintain legacy products and legacy format from the past, or to start exploring new efficiencies in terms of picture quality and data rates with the introduction of XAVC. And also, as the 4K format becomes more pervasive in the prosumer and professional level, then we have this new tool, which is either RAW for production or XAVC intra-frame compression at 4K. These are some of the products that are already introduced in the market. We have been introducing this product for probably a year and a half. And this XAVC chipset that I mentioned in the beginning of the talk is already installed in this product. Therefore, even though I am currently using my format in the form of MPEG, I can easily just, in the very near future, switch to the use of XAVC if the application requires it. Probably you're aware that we introduced last month the first professional 4K handy camcorder. This device uses the XAVC chip and is capable of reaching 600 megabits, 4K at 60 progressive intra-frame compression. And its sibling in the prosumer-consumer world is almost identical physically, but it has different functionality. It can reach 3840 by 2160, which is quad full high definition, and it can reach up to 60 frames progressive also, but this time using long GOP compression, XAVC. It can reach up to about 150 megabits per second. These cameras employ a new memory, which is XQD. It's being used by many manufacturers, and it has capability at this moment up to 1.3 gigabit per second. The reason why we switch between intra-frame or interframe is probably easily understood by noticing the different requirements between the professional applications and the consumer application. In intra-frame at 600 megabit per second is very heavy data rate. The file size is very large. Therefore, we quickly consume a lot of the memory space, and therefore giving me only minimum amount of time for recording. In the consumer world, the levels of picture quality do not have to reach the levels that we have in professional, although they're expected to be very high anyway. But most important is to have a long duration of recording. Therefore, as you can see in this chart, the 14 minutes that I could have in 64 gigabyte XQD employing XAVC at intra-frame compression now can be expanded 4 times to 56 minutes. This is the benefit of the long GOP. It's a factor of 4-to-1 expansion in recording duration. And also, these cameras are capable of reaching very high levels of picture quality, 1080 60p, employing XAVC, a long GOP, up to 50 megabits. As I said, the first implementation of XAVC in the market was embodied in the digital electronic cinematography cameras, the F5 and the F55, which are very popular cameras that can be switched. They are multi-codec cameras, can be switched between MPEG2, XAVC, RAW, and using external recorders. Our PNW 400 is a recently introduced memory camcorder, very popular and extremely powerful in performance. The chip set that we use in this camera, which is part of the XCAM memory lineup, is still MPEG2 because the device is made to operate using MPEG2 up to 50 megabits per second. But very soon we will activate the XAVC long up operation in this camera for interlace. Therefore, it's up to the end user to decide to future-proof its contents by moving to XAVC or to remain with the legacy codecs of MPEG2. These are our studio decks that complement the XCAM camcorders, also implement XAVC algorithms if desired by the end user. Both the studio unit and the professional media station, which is a hybrid station capable of reading and writing optical disc, S/S memory, as well as hard drive and solid-state drive, we have the freedom to select MPEG2 or XAVC for encoding and decoding. A new server that is actually being introduced this month into the market, this is an XAVC server that has a multi-port. It has 4 ports, and these ports can be 4K or high definition and can be completely mixed in any form. I can have one port being 4K, the other port being HD, and this was designed exclusively around the implementation of XAVC intra-frame. Therefore, if you are recording HDTV full 1080 interlace, it will be around 100 megabits per second. If you're dealing with 4K 60 progressive, we will be using XAVC intra at 600 megabits per second. These servers come with 2 terabytes of storage that will give us about 5 hours of 4K at 60 frames per second, 600 megabits per second. This server is a critical part in the family of 4K live production equipment in order to record and implement full production, but for live applications, not only for digital cinematography, but for applications to sports. We also have a very simple and straightforward S/S player that has an XAVC decoding chip. This unit can be installed at the back of our monitors, and with a very simple GUI, we can select the clips, we can delete, select, using the controls embedded in the monitor. Therefore, this is another implementation of the XAVC chip in this portable player. And another one that was introduced in the market about 2 months ago is a wireless adapter. This wireless adapter receives basically a BNC signal, a coaxial cable, a high definition, and inside this device we have an XAVC chip that is capable of recording a proxy version of the high resolution material that resides in the camera. And we have, at this moment, 3 levels of proxies, 1 megabit per second, 3 megabits, and 9 megabits, with different resolutions of the proxy video. The wireless adapter serves as a gateway between the high-resolution camcorder and smartphones and tablets so that we can remotely operate these devices. And once the proxy is recorded, we essentially transmit the proxy, we FTP the proxy to the broadcast center or to the cloud, where the end user or the receiving end can select which frames to select, and then as subsequent, we can send the high-resolution material from the field back to the broadcast center. Of course, we plan to introduce XAVC in all aspects of broadcasting, and one key aspect is archive. And with the quality exhibited by XAVC is extremely high, and many have said that this is an ideal mezzanine compression that could serve very well for final repository of a finished material and programs into our archiving systems. Then who adopts, who follows the introduction of XAVC by Sony? Well, as of today, this is changing day by day, we have about 40 manufacturers that have signed agreements with Sony. And there you see some of the names of the very powerful companies that have expertise in many areas of workflows, not only for content creation, but also for transmission. And in the beginning, we had to approach these manufacturers that you see here in this slide because we needed them to be able to fully embrace the compression and decompression of XAVC streams, which are, as I said, open format. And they very rapidly adopted software solutions that are now capable of decompressing much faster than real time the XAVC streams. The second phase of this program of introduction of XAVC is now we are talking to broadcast manufacturers for playout transmission applications. Again, to facilitate that, we are providing SDKs as well as hardware solutions so that all the manufacturers can easily embrace the use of XAVC. Then our goal is to push, as time goes by, the use of XAVC as a complete mezzanine compression all the way from ingest to final playout and archive. As I said, to facilitate the adoption of XAVC, Sony has decided to create hardware solutions. The lower one, the MSQ211, is a daughter card very similar to the MSQ201 that we used to have for MPEG years back. This daughter card supports up to one channel of 1080 60 progressive, and you can select to compress and decompress either MPEG2 or XAVC. The other card, the XAVC video card on top, is capable of handling one channel of 4K by 2K at 60 frames per second, or 4 channels of 1080 60 progressive. And the relation between manufacturers and Sony is strictly on an OEM basis. We are just distributing these hardware codecs to facilitate new transmission applications. Then, as you can see in this slide, the workflow is very similar to today's MPEG2 using the MXF wrapper. But instead of using the 50 megabit or 35 megabit per second that we have in MPEG2, now we have the choice of using XAVC long op or XAVC intra-frame compression. But otherwise, it's identical in terms of file format exchange. For 4K, the wrapper will be the same as the MXF or P1A, but in this case, now the signal that is being compressed is actually 4K or 1080 60 progressive or full quad, full high definition. And in the area of feature film production, there's going to be a variety of file formats. In some cases, we're going to have uncompressed with DPX wrappers. In other cases, we're going to have RAW. And they will have to be exchanged and transcoding between XAVC and other operations such as color grading and editing. Well, just to conclude, I hope I was able to convey to you the power and the great hopes that we have with the introduction of this new codec, XAVC, which, as I said, is the most sophisticated implementation of H.264 at the level of 5.2. We are going to employ this codec to expand our family of XTCAM by giving us new applications and new levels of picture quality at lower data rates. We will be able to finally answer the dream of some broadcasters that would like to reach 60 progressive, 50 progressive long op at low data rate of 50 megabit per second. And for all those new applications that go beyond high definition, such as high frame rate and 4K, XAVC is ready to answer those applications. Then this is our evolution from today's high definition to the world of 4K and beyond. Okay, this concludes my presentation. And if you are in need of further information, please log in to www.sony.com/professional, where you can find not only this presentation, but other presentations related to various applications of Sony Professional. Thank you again.